So this is the magnitude scale, which is based on apparent brightness. So remember that that means it's a function of distance. So you can see if you look along the left that you have a greater number to the top and a smaller number here on the bottom. So you can see that our sun has a value of negative 26.7. That means that it's very bright because it is close. But if we put everything at the same distance, and astronomers have given this arbitrary distance of 32 light years, so that would give us the absolute magnitude. So if we put everything at 32 light years, the sun would only have a magnitude of 4.8. But notice that our naked eye limit is 6, so we would barely be able to see the sun at 32 light years away. So you can see that the full moon has a value of negative 12.5. So if we put that at 32 light years away, it would be like way up here. So this is a logarithmic scale. So with every increase in a magnitude of 1, you get an increase in luminosity or brightness of 2.5. So for every change of 5 magnitude corresponds to 100 in apparent brightness. So you're not just changing by a factor of 1 for every change in magnitude. And for our brightest stars in our sky would be somewhere around here. So Betelgeuse, Alpha Centauri, Sirius. So everywhere somewhere around a value of 0 would be our brightest stars in our sky. So Sirius at negative 1.5 is about the brightest naked eye star that we can see. So the lower the number, the brighter the object. So here are some bright stars in our sky. So here you can see Rigel under 1. So generally, like what we would consider our bright stars would be somewhere around 0. So from negative 1 to 1. So these would all be pretty bright stars in the sky. So the reason that stars are so much fainter the further they are, besides it being kind of intuitive, is because of the inverse square law. So the further something gets away, the light source is essentially spread out as a function of the square of its distance. So if we can think about, here's our light source, and as we get further away, if we can imagine imaginary spheres around it, so if we get 2 spheres away, if we double the distance, you square the function of that sphere, so you essentially spread it out over 4. And if you get 3 distances away, you square the 3 and you're spreading it out over 9. So you're essentially just diluting the light source. So by the time you get to Jupiter, you're only getting 5% of sunlight. So solar panels on spacecraft wouldn't even work past the orbit of Jupiter. So obviously stellar size is also going to have a function in terms of brightness. So if we have B that is twice as large as A, it's obviously going to be brighter. But it's going to be, this should be a squared right there. We have a proportional relationship between the luminosity and the radius. So if you square the radius, that gives you a value for your luminosity. So a star that was twice the radius would actually be 4 times brighter. So if we look at Polaris, which is our North Star, which is about the same spectral type as our sun, it's actually 10,000 times brighter than our sun. So because we have this relationship of luminosity is proportional to the radius squared, if we know that it's 10,000 times brighter, we can just find the square root of that luminosity of 10,000. And we know that Polaris has to be 100 times larger than our sun. So you may have to know how to go back and forth like that on your test. So you would either square it or find the square root. So we can't image most stars unless they're close by in our solar neighborhood. So by looking at stellar spectra, we can determine a temperature. And from that, we can infer what the size is. So we've already talked about the relationship to radius. And then if we multiply by the temperature fourth, we can come up with generally what the size is. And generally our classification of stars is giant stars, dwarf stars, or supergiant stars. So, and giant stars would be 10 to 100 times greater than the sun. Dwarf stars would be equal to or less than our sun, and supergiants would be greater than 100 times the sun's radius. So here is a picture. So here is an image of a brown dwarf surrounded by the orbit of Saturn. So this would be in the infrared. These are really tough to image because they're low luminosity, low mass. And this is the minimum mass limit for any star. And I'm sorry, my picture got moved here. But in order to actually have fusion happen in a star, which is what signals the birth of a star, you have to have 8% of the sun's mass, which is 0.08 the mass of the sun, which is the lower mass limit for any star. So here we can see in the visible, and then the same image in Orion's belt in the infrared. It's much easier to detect these. So by looking at a star's temperature, we can get a lot of different information about a star. We can determine where in its life cycle it is, and also what sort of fate it's ultimately going to have. So see if we could look over here at the constellation of Orion. We can see Betelgeuse is a red star, Rigel blue, and in this picture we've got various different colors of stars. And that can lead us to our temperature classification. So there's 7 general categories of stellar spectra, and these correspond to different temperatures. So we can see that our hot stars are over here, our type O, our cool, our type M, and there is a really ridiculous acronym that goes along with this. It is O, be a fine girl or guy, kiss me, because you may need to know what the order of spectral classes are. And our sun is a spectral class G star, so because it has, as we've already said, a surface temperature of 5,800 Kelvin. So it's barely hotter than our class M's, but it's significantly cooler than our class O's. So here again we can see our bright blue stars and our cooler red stars. And our stellar spectra is what gives us all of the information that we have about stars. So remember that these dark lines are our absorption features. So here we have decreasing temperature towards the bottom. So here is only 3,000 K. And you can see that we've got much greater absorption in the lower wavelengths and the shorter wavelengths for our cooler temperature stars. So as we increase in temperature and then luminosity, we have less absorption features over here in our shorter wavelengths. So this is telling us the chemical makeup. This is not based on temperature. Color is based on temperature. So some of our key concepts that we've already covered that I would expect you to know is our distance, our parallax, what that inverse square law is and how that relates to distance, our sizes, what information that gives us, and then each of these stellar measurements. Oh, one other key thing that I want you guys to know is that for your solar observation, I won't be announcing this in class, so kudos to you for actually listening and watching. For the solar observation, I had originally said you needed 6 weeks of observation. If you're watching this, I'm cutting it to 3.